what we can get to, talking about gases. So we talked about gases on Friday, and we said if this is our box, I always, when I do gas law problems, I usually draw a box, and I draw my little particles in there, okay? And then I draw them with motion because they have a lot of kinetic energy. And if I want to fully describe the condition of the gas particles in there, I need to say the pressure that they're banging against the side of the container. I need to say the temperature at which they're existing. I need to say the volume that's containing those gas particles, and I need to say how many gas particles there are. And we do how many gas particles there are by N, the number of moles. Okay, so those 4 things. So just a little bit kind of cleaning up things. The temperature, we talked about temperature way back when, and there are different temperature scales. There are 2 metric temperature scales. There is the Kelvin scale, or sorry, there's the degrees Celsius scale, that's metric, and there's the Kelvin scale, that's also metric. And as it turns out, we're going to have to stick with the Kelvin scale. The Kelvin scale, whenever we do gases, whenever we do gas problems. What's that? Oh, there's the Fahrenheit, yeah, sorry. For you non-science people, there is the Fahrenheit scale that we all live by when we want to know what the temperature's like outside. But when it comes to the metric scales, we have to go with the Kelvin temperature scale. And I think we talked about this before, that this is, and I have a graph either today or Wednesday that's going to show you that gases actually kind of are a way to identify where that absolute zero temperature is, where all molecular motion stops. Okay. So if you're looking for things to put on your sheet, I almost call it a cheat sheet, but you're not cheating when you bring it to your final, okay? When you're looking for things to put on your sheet, you might want to put, let's see, which one? Probably this one. If you are given the Celsius temperature, what you do is you add 273.15 units, okay, to get Kelvin. Now, we don't talk about degrees Kelvin, we just talk about Kelvin units. And there's a reason for that. I can't think of it right now. And if we want to go back from Kelvin to Celsius, we, subtract 273.15. And I always have to concentrate, is it add or subtract? So if you're like me, you might be like that too. So either probably Wednesday, but maybe today, we're going to get to one simple sort of, looks like a physics equation that connects the pressure of a gas, the volume of a gas, the temperature of a gas, and the number of moles of a gas. It's called the ideal gas law equation. And the ideal part of it actually is gases are behaving ideally. They're not misbehaving otherwise, but one of the things about gases, we said, is that gases have low densities. They basically fill their container, all that stuff we talked about on Friday. So, but if it's behaving entirely ideally, every little gas particle is independent of the other little gas particle that's in its container. There are no forces between them, intermolecular forces. The other thing, and this is kind of weird, because we said that all matter has mass and occupies space, right? Okay, gas particles do occupy space. But if they're behaving ideally, then basically the container that they're roaming around in is so large relative to the volume of the gas particle that we say the volume of the gas particle is negligible. I know it's just kind of a little game we have to play, okay? But the gas particle volume itself is negligible, which kind of goes against all matter has mass and occupies space, but that's okay. So the whole thing about little gas particles are independent of each other, and sometimes I think we in our lives are independent of anybody we run into. Okay, that happens in our lives if we're going very fast, if we're very busy, and that also happens with gas particles if they're going very fast at high temperatures. Makes sense? And the whole volume thing, okay, if a gas is behaving ideally, we say its volume is negligible. The whole volume thing works if basically those gas particles have like so much room to roam that their volume is minuscule compared to that. Now, if gases are compressible, so if we take this volume and we squish it down, squish it down, squish it down, squish it down, okay, that's the volume they're roaming around in. At some point, we actually do go ahead and get the gas particles do have significant volume compared to the container they're roaming around in. And that happens at high pressures. Okay. So if you want your gas to behave ideally, go ahead and have it at high temperatures and go ahead and have it lots of room to roam around at low pressures. Okay, so those two conditions automatically make your gas behave ideally. So again, we're going to come up with something called the ideal gas law equation. I think it's on the slide coming up. And that's the ideal part of it. So here is the ideal gas law equation. And it links, look, if you've taken physics at all, it kind of looks like a physics equation where each one of those letters represents a variable. So P is pressure, V is volume, N is number of moles. I'm going to have to get to, I don't know if today I'll get to it or I'll get to it later, but I'll go ahead and tell you. T is temperature. This R is actually a constant. It's called the ideal, go figure, gas law constant. Sometimes maybe you're like me, you wonder what it'd be like to live like, 200 years ago, that sort of thing, when they were still finding out things. But at some point, somebody smart said, all gases have this relationship in common, and they all vary by a certain constant, R, the pirate's favorite constant, ideal gas law constant. Okay. So on to part 2. Just kind of builds on that. Oops. Maybe I do this. Really? Oh, yes, you can. Oh, I know I can't. So I'm still just I'm gonna talk about kind of descriptive stuff. It's kind of like, oh, gases, that makes sense, sort of stuff. Okay? So, for instance, okay, there are these 3 laws, and they all happen to be gentlemen who came up with these laws. Not that women can't do it. Okay, but each of these laws deal with gases, and they took the 4 variables, and they picked 2 of the 4 variables, held the other 2 constant, and saw how they changed. So it kind of looks like this. Okay, Boyle's law. And we talked about, I know, on Friday, that this symbol right here, the infinity symbol with a byte taken out of it, that's proportional. Okay. So what Boyle's found is that the volume is directly proportional to the inverse of the pressure. If you don't want to kind of screw around with that inverse, you could say that the volume is inversely proportional to the pressure. And we talked about this on Friday. We said if you take a container that has gases in it, okay, and we're going to make our container smaller, our volume smaller, what happens to the pressure? Yeah, the pressure goes up, exactly. So because volume is less, pressure is more, that's the inverse part of what we're talking about. And that's Boyle's law. I just get my 3 laws mixed up. Okay, cool. So, it's a math thing. It's a mathematical thing. If you want to replace the proportionality symbol with an equal sign, you can do that. Okay, but you have to introduce a constant. So we said that volume and pressure were inversely related. So that means if in the same system, assuming that temperature and number of moles are the same, if you multiply them together, you're going to get a constant. What does this mean? Well, for instance, if the volume goes down, the pressure will go up. So that multiplied by each other, they are this constant K. And I'm just going to leave it a generic K for now. Okay, that's all that means. All right, that's Boyle's law. Some examples of Boyle's law. So, for instance, if you have the traditional tire pump, you're pushing down the plunger. Okay, you're decreasing the volume, and what happens to the pressure? It increases, yeah. These are some of my favorite things coming up with marshmallows. You'll see here in a minute. This actually is a part of a mercury barometer system. Okay, it's simply saying that as you increase the pressure on the liquid mercury, the volume will decrease. That's what's going to happen here. Increase pressure, decrease volume. The gas volume is right here. I looked at these for a little while. That's kind of fun. Okay, so they're inversely related. So we have this figure from your textbook. Let's kind of look at what it says. Along the y-axis, we have volume, okay? And let's go ahead and decrease the volume. So let's go this way. Decrease the volume, okay? And then along the x-axis, we have pressure. So as you decrease the volume, can you see where you're increasing the pressure? Decrease the volume, you're increasing the pressure. All right. I think we might have looked at these before. These are kind of clever. This one actually has a little, this is a pressure gauge right here. It's measuring how the force per area of those gas particles. This right here is a free moving sort of piston, like kind of like your tire pump. It's like a plunger thing. So it can move up or down, and actually it can move up or down right now based upon the mass you have on top of it. So that little gold thing is a weight. So it's just saying, okay, if it's free moving, then kind of that weight balances out the pressure that the gases are exerting on it. Okay? So if you were to call that A and that B, what the second one, what's the difference of the weight? What do you think happened to the weight?
Twice as large?
Yes, it does look twice as large. And in that sense, it's like creating a pressure. It has more of a pressure that the gas particles have created in order to support it from squishing all the way down. So increase the weight, increase the pressure. What happened to the volume? Increase the pressure.
Down.
Yeah, it went down. Yeah. So that's showing you the inverse relationship. And actually, like I said, I think this is kind of clever. They have this cute little pressure gauges. So you can kind of see the pressure gauge go up. And I heard somebody say twice. It kind of looks like we're having twice the pressure, half the volume. That's totally true. Let's go ahead and do a little thing. So we said PV is equal to K, according to Boyle. So let's go ahead and take our pressure, which is 1 atmosphere, times our volume, which is 1 liter. Okay, so that equals 1 liter atmospheres. Looks okay? Over here on the other side, I'll switch to green. We're going to take our pressure, which is 2 atmospheres, times our volume, which is 0.5 liters. And what number do we get? We get a value of 1, don't we? 2 times 0.5. So that's 1 liter atmosphere. So that's what it means. If you have the same, if you isolate it, the number of moles of gases are fixed, and we're assuming it's the same temperature. Okay, that's kind of what that means. Kind of a cool sort of mathematical situation. I love gases. Okay, so this one starts with the letter E. What do we call this type of flask? Erlenmeyer, yes. That's an Erlenmeyer flask. Sometimes it's called an E flask because I can't pronounce Erlenmeyer sometimes. This actually is a thick-walled Erlenmeyer flask with a side, with a, what do they call that?
Nipple.
Yeah, it looks like a nipple. I can't remember what they call it. Sidearm flask? I don't know. But yeah, it's definitely just a nipple thing, and it's got a gas tube connected to it, okay? So here in a minute, we're going to go ahead and seal that thing up. The reason it's thick-walled is so that we can go ahead and pressurize it and draw a vacuum, and it won't crash. That's a good thing. And then the glassware so far, this semester's really done pretty good. So the gas of interest, sometimes in these little gas problems, and you'll see this on Thursday, it's hard to know what the gas of interest is. And the gas of interest is actually this gas that's trapped in that syringe. So syringe, the handle of the syringe is like a plunger. It can go up and down. Notice we have that gas is trapped from like going out this way, and it's also trapped from this little stopper here. All that stopper's doing is making it so the gas can't escape. All right. So let's go ahead and put a tire pump. Oops, sorry. Before I go on, I feel like a magician. What would you say the volume, if this is milliliters, 1, 2, 3, 4, about 5 mils? All right. So we're going to increase the pressure. We stopped it, and we increased the pressure. Now how many milliliters is it?
3.
About 3, yep. We increase pressure, decrease volume. Yep, I think we're going to do one more. Increase pressure, decrease volume some more. Exactly. I mentioned marshmallows. Here they are. Oh, I love marshmallows. So those are just almost pure sugar, right? Sugar and air, would you believe it? Okay. So here we are, minding their own business. Okay. And the first thing, we're not going to do the tire pump. We're actually going to draw a vacuum. Okay. So we're going to draw a vacuum, which would lower the pressure. Lower the pressure. So what should happen to the volume? Yep. Was that not cool or what? I'm sorry, but it's the end of the semester. But I just think that is so cool. You lower the pressure, you increase the volume. And then these poor little marshmallows, they switched from a vacuum to the tire pump. So you increase pressure, what happens to volume? Yep. I know. There's your little confectionery delight right there. So again, this is Boyle's law. Now, the thing that's different along the x-axis, y-axis, is we're not plotting volume. We're actually plotting 1 over volume, the inverse of volume. So the cool thing here is the inverse of volume should be what? Directly proportional to pressure. So the way this works is the gas of interest is again in your syringe, and to get different pressures, we're just going to go ahead and put shot in there. So here we go. That's without any weight. That's with 500 grams of shot. Okay. So we are increasing the pressure. What should happen to the volume? Wait, increasing the pressure. Yeah, volume should go down. Okay. The volume should go down, but guess what? The 1 over volume goes up. The inverse of volume, exactly. That's all this is. Okay, that was, this is 1,000 grams, and this is 1,500 grams. Okay, so notice that, and we do this a lot in science. If there is an inverse relationship, we go ahead and plot the 1 over it, so that we have a direct relationship. Okay, so that was Boyle's. Now we have Charles' law. So we have a direct proportionality, because it's not over the inverse, it's directly related. And I think we talked about this on Friday, I'm not sure. And this makes sense about gases too. If you're going to make the gas stay at the same pressure, okay, and you're not going to change the moles, what happens if you heat it up? What happens to its kinetic energy? As you increase temperature. Yeah. If you increase temperature, it gets more kinetic energy. And we're going to go ahead and leave it at the same pressure. So if that's the case, your container needs to swell, get larger. Okay, so if you increase temperature, you increase volume. You decrease temperature, you decrease volume. Okay, and this, I think I might have said with the balloon, you buy a balloon at Hy-Vee for somebody, and it's cold outside, and the balloon kind of shrinks because it gets colder. Okay. So again, we can go ahead and introduce, since they're proportional, we can introduce some sort of proportionality constant K. Now you'll be like, well, is this K the same K as what we talked about before? No, they're just generic Ks. Okay. So since they're directly proportional, this is how they end up being. Do you see where volume goes down, temperature will go down, and we'll get the same ratio. If volume goes up, temperature goes up, and we get the same ratio, we get the same number. So that's how that works. So I think I just have one with Charles' law. So Charles' law is temperature and volume. So I don't have any, but, well, we have some. What's the most abundant gas in this room? It's not oxygen.
Nitrogen.
It is nitrogen. Good job. Yeah, if we were to take this nitrogen and cool the nitrogen gas particles down and probably pressurize them, we can actually get liquid nitrogen. That's how you get liquid nitrogen, I know. It's very cold and very cool. And so here we have these, they're not marshmallows, but they are balloons minding their own business. Okay? So as we cool them down, what's going to happen to the volume? Lower temperature, yeah, lower volume. And that's all this is. So as we put those adorable little balloons in that little Dewar flask with the liquid nitrogen, they still have their gas particles, but they all shrivel up. Okay? And then the last one is we're going to go ahead and take these back out into room temperature. So the gas particles are still in there. I just think that's so cool. Okay? Yeah, I know. So what's going to happen now to, as we warm them up, what's going to happen to volume? They're going to expand back up again. This last one reminds me of if you've ever ordered like ants through the mail or something, like for an ant farm, they oftentimes come with some sort of like little coolant sort of thing. so they're like really chilled for the trip. And then you get the ants out and get them to room temperature, and they start like scurrying around. Hopefully where they're supposed to scurry around. Okay, so that's Charles' Law. I think that is neat. Okay, so the whole idea of increasing temperature, increasing volume, actually is the crux of why these wonderful hot air balloons do what they do. Okay, here is a look at Charles' Law. So let's go ahead, let's start here along the x-axis. Go from left to right, we're increasing temperature. Okay, increasing temperature, increasing volume. You can kind of see that. So you increase temperature, you increase volume. You decrease temperature, you decrease volume, just like we saw at the balloons. Okay. At some point, are you going to be able to get a gas that basically has a zero volume? Shouldn't. But that temperature at which a gas has zero volume intersects with absolute zero. That 0 Kelvin, okay, so that's why 0 Kelvin is one reason why 0 Kelvin is so important. So this is showing you the gas helium. This is what I tried to say a minute ago. We're going to go ahead and cool that gas down, okay? As we do so, they have less kinetic energy, so they occupy less volume at the same pressure, less and less volume. And at some point, like I said, you have a volume of 0. Now that volume of 0 corresponds to a temperature of negative 273 degrees Celsius. It also corresponds to a temperature of 0 Kelvin, which of course is absolute 0. Did I already complain to you guys about, like, when this summer we went to Chicago and went to the planetarium, and they had like little things about all the planets, and there comes some students. They had some things about the planets, and one of the things was what their temperature was, and one of my things was they said the temperature, they gave the scales, and the coldest temperature they had was negative 300 degrees Celsius. I know, see, you're like me. I was like, really? Negative 300 degrees Celsius. I mean, the coldest temperature anything would be is negative 273. So I haven't written a letter yet, but I'm fixing to. I took pictures of them and everything. I thought about contacting Neil deGrasse Tyson and saying, dude, we need to work on this.
Do it.
I know.
That'd be awesome.
Well, we'll see. We'll have the nerve. So that's a good place to stop. And we'll pick up with Avogadro's, still need to talk about Avogadro's law. And we'll combine them to make the ideal gas law equation on Wednesday.
Maybe out here in random.